Hey, this is Jim Bergmann with MeasureQuick. On behalf of AccuTools, I'd like to do a little bit of a presentation today on vacuum and the basics of evacuation, and really answer some questions about why products like True Blue. I think there's some mystery on there why we'd want to do that. Evacuation principles and processes is where I want to start, and there's really three knowledge plateaus we want to talk about. The things which some of us know something. You know, we talk about like things we might have learned in high school or grade school. We think we know a little bit about the earth and vacuum. Things which some of us know a lot. You know, some of us have been doing this for 20 years and we think, wow, I've been doing evacuation for so long, how could anybody teach me anything? And then there's the things which none of us know enough, and that's really what this whole book is about. This review of vacuum for service engineers is literally written back in the 1960s. And I think it's interesting, a guy I know, Dan Houlihan, coined the phrase the dead men. And it's really the long gone authors that taught us a lot about the lost arts. And evacuation really is one of those lost arts. We just forgot how to do it as an industry out there. So we're going to start with the basics of vacuum 101. And here's probably one of the biggest myths I want to dispel is vacuum pumps don't suck, right? Now, when you think about this, I got really confused on this a few years ago. I was actually surfing through some videos and ran across one of people that thought, believed in flat earth theory. And one of the things they talked about was how the vacuum in space was so deep that it was going to suck away our atmosphere or pulled our atmosphere up towards space. And it really, I should have thought about it early on because I've been teaching the high school programs for so long, but it didn't click with me at first. But pressure always pushes one direction, and that's from high to low, right? It always pushes from high to low. Pressure only flows in one direction, okay? Vacuum pumps just create that area of low pressure to flow into. Pressure rushes into that area of reduced pressure. So when we're talking about evacuating a coil or evacuating anything else, the vacuum pump is actually creating an area of low pressure, and then the pressure that's in that coil gets pushed into our vacuum pump. Just like air gets pushed into a vacuum cleaner. We think about, we're vacuuming a floor out there. The vacuum cleaner creates an area of low pressure, and then the atmosphere that's at the carpet pushes in. So we're actually pushing the dirt into the vacuum cleaner. We're not pulling it inside. Pressure always travels again from high to low. Here's another important thing to understand is when the pressure difference becomes too low, the pressure flow will stop. And that's a really important concept to understand. Now, vacuum is just empty space, and we're talking about, our upper atmosphere, about 56 miles up. We have the deepest vacuum that we can, a deeper vacuum in space, 56 miles up, than we can ever achieve at sea level, all right? Now, if you think about, we said earlier, pressure only goes from high to low. So how does this work? Well, the Earth is heated by the sun. The sun is the only new energy that we ever get, and that is superheating gases at the earth level, and that's what's creating our atmosphere. And then that atmosphere is simply pushing, the pressure generated down here is pushing up into space. So about half the weight of our total atmosphere is about 3.75 miles up, and about 3/4 of the weight, a quarter plus half, is 7 miles up, and beyond that it gets almost really, really deep vacuums at that point. And gravity pulls the gases back down towards Earth, but the pressure is pushing up. So at this point, we have our highest pressure down here where the gases are being generated. They're pushing up into space. The Earth's gravity is pulling back down, and it's just as high as we can push against the gravitational forces of Earth, right? That's all it is. At 60 miles up, the pressure becomes so low that there's no force left to push it into space. Atmospheric pressure versus vacuum. This is really what we call the first plateau of knowledge. And here's the key things to understand. Vacuum is any pressure lower than atmospheric pressure. That's all it is. It's just whenever we're talking about going into a vacuum, it's any pressure lower than atmospheric pressure. You might hear words like deep vacuum. Well, there's no such thing as a deep vacuum. It's just a relative to the atmospheric pressure. So vacuum is vacuum at the end of the day. Nature can create a higher vacuum than can ever get attained by man if the state of vacuum is also that of low absolute pressure. So you're going to hear all these different terms. And vacuum is always measured in units of absolute pressure. So 0 psia, that's a perfect vacuum. That means all the atmosphere has been removed. Negative 14.696 psig. Now what we're talking about is against a relative pressure, right? 0 psi relative. That we would have negative 14.696 psig. That's, again, down at a perfect vacuum. or 29.996 inches of mercury, or 0 microns of mercury. All these are just different ways that we describe a perfect vacuum. In practice, though, we can only achieve a partial vacuum. We can never achieve as deep of a vacuum as we can in space. We cannot remove all the molecules. And evacuation is simply the removal of the free air. That's all we're doing. We're just taking the free air away. That's oxygen, nitrogen, other gases, and also the water vapor that's attached. By definition, going back to the Vacuum for Service Engineers book, our work becomes involved with air leaking into a system. We refer to this as free air, and that's the unconfined atmosphere which we freely breathe, in contrast to compressed air, which is mechanically compressed, right? So it's just the air in this room is free air. Gases have molecular activity. Now, this one's an interesting and probably a really hard concept for some people to understand, but hopefully I'll get it explained to you here. If I have a 100 cubic foot tank of water, and I have a pump that pumps 10 gallons per minute, or 10 cubic feet per minute, in 10 minutes, we'll have emptied all the water out of that tank, right? 10 times 10 is 100. If we run it for 10 minutes, it's going to drain all the water out of the tank. Well, atmosphere is completely different. If we have 100 cubic foot of gas and we exhaust at a rate of 10 CFM, whether we pump for a month, a week, a year, or a minute, there's still 100 cubic foot of gas left in the tank. It's just fewer molecules. We can never empty all the atmosphere out of that tank. So there's fewer and fewer molecules, so there's a lower pressure, and then it's in a direct proportion of the molecules removed. The remaining molecules will occupy the entire space, and that's what builds up a vapor pressure. So we isolate a system. We'll talk about this later. We'll see this gradual buildup of pressure. That gradual buildup of pressure is just a pressure created by the molecules that are left. No matter how long we evacuate that, we cannot pull all the atmosphere out of that tank. Vacuum is also a really poor conductor of heat. Gases, as the molecules are removed, there's fewer and fewer molecules left to bump into each other, and this is the reason vacuum is used for insulation of a thermos, right? And if you look at a thermos, what we have here is we have these vacuum chambers around it. So it's glass typically, and then we have vacuum in between that glass. And then also you have this like silver painted on the inside of this, and that silver is used to also block radiation. So what we've got here is a vacuum does not allow conduction or convection, and then the silver blocks the radiation in there. So we actually block by all three. Conduction is molecule to molecule, where it's actually touching and transferring by touching. Convection means transfer by the air. We've eliminated that. And then radiation. And that's actually also the way that these thermistor vacuum gauges work here. So what we've got here is this is a thermistor, and if we were to look at this, this is a vacuum gauge. What we're talking about is the sensor's literally inside this silver tip right here, okay? So that is magnified under a microscope so we can see it and see the size of the sensor. But that's literally mounted inside here. So that's how small that really is. This little black dot here is about the size of a grain of pepper on there. And this little black dot is the thermistor, and it gets up to about 300 degrees Fahrenheit. And what happens here is as this is heated up, heat travels by radiation, conduction, and convection away from this thermistor to the outside walls of that connector on there, the aluminum port we connect to. And the rate of heat transfer is affected by a number of molecules, the amount of gas around that sensor. So as we have a lot of gas around here, we're going to have a lot of heat transfer, and we got to put a lot more current through this thermistor in order to keep it at 300 degrees. As the gas molecules are removed, we have fewer and fewer of them in there. The heat transfer goes down, and now it takes less current to keep that thermistor at the same temperature. And that's all that how a vacuum gauge works. It's really quite a simple thing when you look at it at the end of the day. So how does a vacuum pump pump? Well, gases are always seeking equilibrium, and the vacuum pump simply acts like a trap for the gas molecules to flow into. Let's start a little video here. We'll let it run as we go here. But the pump creates an area of low pressure at the inlet for gases to flow into. And this will start here in a second. So the gases are traveling down inside the pump. It's swinging around, grabbing those gases, compressing them up, and exhausting them through the oil. Now this gray level here is oil in your vacuum pump. And that's when we exhaust it out here, a small amount of that moisture also gets trapped in the oil, and that's why your oil might turn a milky color. But this is just sweeping away the molecules and creating that area of low pressure for the gases to flow into. When this pump can no longer pull, in other words, when this seal right here on the edge is an oil seal, and when that oil reaches its ultimate vapor pressure and a pump can no longer pump any deeper, we've reached a state of equilibrium, right? And that's typically around the 10 to 25 microns for a decent pump. This one here I have on the table here, this Navac pump's rated at 5 microns, so it'll pull down a little bit lower with the right oil in it. So the hose is just simply an extension of the vessel being evacuated, and this is really why it's so important. Remember, the vacuum pump's sweeping away, creating the area low pressure, and now the pressure inside this vessel is pushing up through the hose and into the tank. So the larger the hose is, the less pressure we have drop due to friction we have in there. And the lower the pressure goes, obviously the slower that the equilibrium takes place. But larger connections allow for faster equilibrium simply due to the lower resistance of flow. So we want these large and short because this, as it extends out here, it's just going to slow those gas molecules down as it goes through them. All right, so now let's get into what the lost art of vacuum really is. Now we've gone through the little bit of primer. What we as an industry forgot, and this actually goes back to a review of vacuum service engineers from 1959. This talks about the state of viscous flow. We'll cover what viscous flow means in just a minute, but think of this as the fast flow in there, right? And here's the paragraph I think that's worth really talking about. That's the conductance speed of 1/4 inch OD refrigeration tubing is too small to be useful as a connecting line in a system. So we'll not even discuss it. Never use it if you can avoid it, as it's too costly and excessive pump downtime. Now this is obviously 1/4 inch OD tubing. We're talking about refrigeration line, which we have is 1/4 inch ID, which is a tiny bit bigger here, but let's talk about how that measures up. So the main reason now, however, the main reason we come to explaining this is the sizing problem, and it's to show the handicap of undersized lines and greatly reducing the pumping capacity of vacuum pumps. So what we've got here is not only do the undersized lines not provide a lot of flow, but they also choke down your pump and reduce the flow down tremendously. The maximum we're talking about here, conductance speed. Though we talked viscous flow, and conductance speed is just simply how fast vacuum flows at a given pressure. So in this case here, we're going to talk about 1,000 microns. But the maximum attainable flow, we're talking about the 3 flows we have are viscous, transitional, and molecular. Viscous is our fastest flow. That means it's a pretty laminar flow. It's just flowing straight out. This is the area that we want to be in. And then we get this transitional flow, which the flow starts to slow way, way down. And then we get obviously the molecular flow, which the flow almost considers stopped. This is literally where a molecule is going in random directions. If one happens to go out the end of the vacuum pump, then we get it out again. And this transitional flow is just simply the space between viscous and molecular. Transitional flow, they're still going in pretty much one direction, but they're pretty much random and bouncing around a little bit in there also. And this, again, that's why that slows that way, way down. So we talk about 1/4 inch hose at 1,000 microns has a conductance speed of 1/2 CFM, all right? So 0.5 CFM. 3/8 hose at 1,000 microns has a conductance speed of 1.5 CFM. So literally, if we took this 2 CFM pump here, right, with 3/8 hose, which you guys might see, like this is a Hillmore hose set here. It's got a 3/8 evacuation hose. It's literally choked down to 1.5 CFM, right? So no matter how big your pump is, if I have a 12 CFM pump or this 2 CFM pump, the pump's choked down to 1.5 CFM. 1/2 inch hose at 1,000 microns has a conductance speed of 4 CFM. Now we're typically talking about a 10-foot length of hose tube here, by the way. I want to make sure that we're talking about that correctly. So these are all at 10-foot lengths. And then we get 3/4 inch hose has a 1,000 microns has a conductance speed of 16 CFM. So typically we're talking about its diameter to the 3rd or the 4th power. So you can see here by just going up 1/4 inch, we went from 4 to 16. 4 times 4 is 16, so it went up to the 4th power. As the pressure drops, the flow decreases. So as we get deeper and deeper vacuums, the flow is going to slow down. And also as the line size increases, we get a bigger line, so does the flow. The flow increases also. So there's a couple of really important things to understand there on the bit different flows and conductance speed in the vacuum. So how does 1/4 inch hose measure up? You know, as long as I've been in this industry, guys have been evacuating through a typical 1/4 inch manifold. Typically these things have 5 foot of hose on them. You know, when we're looking at the total length of the hose, you got to take the length of this one plus the length of this one, you know, so this is how we get 10 foot of hose is typical on there. And so when you're talking about 10 foot of hose on there, it's not an uncommon thing to be evacuating through. But this typical 1/4 inch hose, we cut it in half here just so you could see a cross section of it. It's only 3/16 ID, so it's only a 1/16 of an inch within that 1/4 inch tubing. And then you get over here to our true blue hoses, it's a true 3/4 inch ID. Now not only is the ID larger, but it's also got a lot of better properties. This 1/4 inch hose really has low conductance speed, which we talked about, but it also outgasses. anytime you have rubber, if you've ever taken a set of hoses out, rubber hoses, you get that rubbery smell to them. Well, where's that rubbery smell come from? It's the hose outgassing. It's curing still. It's kicking out chemicals on there. And if those chemicals are pushing out of your hose, we have to evacuate those chemicals. That's called outgassing. Rough interior surface. So if that surface is rough, and then we're talking about a rubber that's been extruded, if you looked at that surface of that rubber, it'd be very, very rough compared to the smooth inside bore of this hose. And that rough hose also has a lot of places for moisture to get trapped and chemicals to get trapped, and so it contributes to the evacuation time. High adhesion properties, which means that it holds water. Once water bonds to it, it holds onto it really well. They also get refrigerant oil contaminated, which means that we're using those for charging hoses, so we're constantly running refrigerants and oils through there, and that becomes contaminated, and that oil then sucks in moisture and bonds to it. And then they're also pinpricked because these hoses are designed for charging. So when we're talking about a charging hose right here, what's happening is that this inner wall is permeable, and this outer jacket would tend to bubble or blister if we were to not pinprick that outside of that hose, and that's what keeps that jacket intact. And then these also have a high permeation rate. Because it leaks out, it also leaks in. So they're really not an engineered solution for vacuum like True Blue is, and that's one of the things that we're going to talk about as we go through the presentation. Now, we talked about flow in a vacuum, the fast flow, the viscous flow, and then the molecular flow. Transitional flow is just that flow in between, so there's really not a good definition for it, but we can tell you where viscous flow ends and where molecular flow begins. And that's really what this slide's about here. So viscous flow ends at 100 divided by D. So we're talking about a quarter-inch hose, a quarter-inch charging hose like we're normally using. The viscous flow ends at 533 microns. This is why it takes so long to evacuate when you're using quarter-inch hoses, because again, to have a flow, we always have to have a pressure difference. Pressure goes from high to low. So if the viscous flow ends at 533, to get that additional, to get down to that 500 micron range takes forever to get down there. We're talking about a true quarter-inch ID tubing there. It's at 400 microns is where the viscous flow ends, versus a 3/4 inch is 133. So you can see, because we're way down in that viscous area at 133 microns, we're going to get a much, much faster evacuation. But here's an interesting thing also, is that there's a point of diminishing returns. Because think about what we're trying to achieve. Typically, we want to achieve, believe it or not, a finishing vacuum of about 100 microns if we can. But a lot of you guys are going to say, well, I only go to 500 microns. And that's because, honestly, I think as an industry, we forgot. And I'll cover that in a later slide here. But here's one of the things I want you to see. At 3/4, the viscous flow ends at 133. At 1-inch hose, it ends at 100. At 1.25 inch, it's only 80 microns. So there's this point of diminishing return where we get a much, much bigger hose, but we don't get that much better performance. And because the vacuums that we're trying to pull, this allows us to still hit those numbers we want to hit, but do it in a lot faster time. Now, this is where the molecular flow begins. And I want to show you we're almost never in this area here, because for quarter-inch tubing, the molecular flow begins at 16 microns. I doubt anybody's ever pulled 16 microns through a quarter-inch line unless you're using copper tubing. For the 3/4 inch hose, for the True Blue hose, we're at 5.33 microns. So that transitional flow is between 5.33 and 133 microns, and that's an area that we can get into, but we're not in there all the time. Now, the other question we get is, wait, aren't the quarter-inch ports the limiting factor? And absolutely they are, but only for a few seconds. And the best way to describe this is we have a traffic jam here. And when you're talking about molecular removement, remember there's only a definitive number of molecules to remove. It's a sealed system. So we're not replacing those molecules with new ones all the time. We're starting out with so many molecules in the pipeline, and as we pull them away, they get sucked out and they're gone. And then we have fewer and fewer to deal with. So at 76,000 microns when we start, there's 760,000 microns at atmospheric pressure. By the time we get down to 20,000 microns, 97% of the work is done. In other words, 97% of these cars are gone. So initially, when we first start the vacuum pump up, this is a slight restriction of flow. If this was a 1,200-ton centrifugal chiller, that quarter-inch port would be a factor for a long time, because it takes a long time to get from 76,000 microns down to 20,000 microns. But in a residential system, this is only for about 10 to 15 seconds that we have this dense traffic. And then we get down into this region here where we have less and less traffic, and this quarter-inch port now becomes less and less of a factor until we get down into here. Maybe we're in the 1,000 micron region where that port may be as wide as 7 freeways wide, because if you think about it, if we had all this traffic and we had to neck down to one lane, well, that would really slow things down. Here, the traffic is moderate, and when we choke down, it slows down just a tiny little bit as you're going through there. But eventually, when we get down to a single car traffic here, man, we can zip right through the toll booth, never even have to stop, because it's just that much easier to flow. So in reality, when we size this port up, there's actually port sizing and an orifice, this is considered an orifice for viscous flow. That's good for about 14 CFM. So that port is really, really not the restriction when we're talking evacuation. But what we do have to talk about is overall pumping speed and system losses. And again, going back to vacuum for service engineers, they want a conductance speed of the manifold versus that of the pump to be 4:1. All right. So what I've got here is just simply SS is speed of the system, SP is speed of the pump, CM is conducting speed of the manifold, and there's a formula there, right? And it's basically saying that if we had a conductance speed, if we had an 8 CFM pump at 1,000 microns, and we connected our true blue hose to it that's got a conductance speed of 56 CFM at 1,000 microns, the overall system conductance would be 7.03. There's always going to be loss, when you connect a hose to a vessel, because the hose creates friction. It ends up being about a 12% loss when we connect our true blue hose there. Now let's contrast that to 1/4 inch hose with a very generous flow assumption. Same thing, 8 CFM pump at 1,000 microns, but now that cuts down to 0.7 CFM at 1,000 microns, which means that our overall conductance speed is 0.47 CFM. So we're looking at 7.03 versus 0.47. Well, 0.47 divided by 8 is 94% loss. So that 1/4 inch hose, we've lost 94% of our evacuation power, let's say, versus 12% with the true blue hoses. The true blue hoses are a ratio of 7.25 to 1 versus 0.006 to 1 with 1/4 inch hoses. So again, this is why it takes so long with those 1/4 inch hoses to evacuate the system. A 20% loss or less is desirable, and you can see with a 12% loss, we're well within that range. But it's not just the limiting factor of the hoses, because we don't often think about, we have 3 things there. We have the pump, and we have the conductance speed of the pump. How many CFM can the pump move at a certain pressure? We have the conductance speed of the hoses. How many CF can the hose move at a certain pressure? But then we also have the system conductance. So system means the lines we're attached to. So if we're on an evaporator coil and we've got 3/8 and 3/4 line, that's also got conductance speed. That's the connecting piping on there. And again, we can calculate the conductance speed on there. So I got, in this example here, I got a 3/4 50-foot line set, 3/4 by 3/8, and a 1/4 inch vacuum line, like a regular set of hoses you'd have here. Well, if we take the conductance speed of the 3/4 inch tubing, that's 3.29 CFM, add that to the conductance speed of the 3/8, that's 0.2, so the total system conductance is 3.49 CFM. That is, when we talk about, for a typical system, a 3 CFM pump is more than adequate, because the system conductance is about 3.5 CFM. So that means that the pump is not the limiting factor. In this case here, we connect it to that 10-foot 1/4 inch hose, which has a conductance speed of 0.2 CFM. The limiting factor becomes the hose. We have a 5 CFM pump that can do 5 CFM at 1,000 microns. We have a total system conductance of 3.49, and a hose here that's choking the whole system down to 0.2. That's the big problem. Now contrast that here, we'll take an 1 1/8 line set and a 1/2 inch refrigerant line and a 3/4 vacuum line at 1 meter and a 12 CFM pump. Do the math again. The 1 1/8 tubing has a conductance speed of 16.65 CFM. Conductance speed of the 1/2 inch refrigerant line is 0.65. Add those together. The total system conductance is 17.3. Now I'm connecting that to a vacuum hose. It's got a conductance speed of 58.8 CFM, because now I'm going from 10 feet down to 1 meter. That's also going to increase our flow. We said, well, remember, larger diameter, shorter length. So when I calculated the conductance speed of that hose, 58.8 CFM, and that means my 12 CFM pump now is a limiting factor. So I can pull a full 12 CFM through this system because I have the right hose and enough system conductance that now the pump becomes the limiting factor in evacuation. So we'll look at true blue hoses versus standard hoses. There's a couple other things you also want to consider, right? In this example here, what I did is I pulled down 3 vacuum pumps. I got actually 3 of them underneath the table right there. and you probably can't see them in the video here, but just take my word for it, there's 3 there. They pull down to 5.4, 8.7, and 7.7 microns. So they're within 3.3 microns of each other. And all I did was connect a true blue hose, an Appion hose, and a 1/4-inch hose to the end of the vacuum gauges and started pulling them down here. And this is about 15 minutes in here just to show you what's going on here. So at 15 minutes in, just on the hose, the 1/4-inch hose is at 1,000 microns, right? That's 14 minutes and 33 seconds, we're at 1,000 microns. At 500 microns here is the Appion hose, and then at 95 microns here, we're at the True Blue hose. So there's 900 microns between the True Blue and the 1/4-inch, 400 microns between the True Blue and the Appion, and remember the pressure difference is what causes the flow. So with this lower pressure that I can create with my True Blue hoses, I'm going to get increased flow, and that's really, really important to fast evacuations. Now this is also logarithmic scale, meaning that different parts of this graph are compressed. So this spread is actually a lot bigger than it actually looks on there, but huge, huge difference in flow on a vacuum. So the next question is, how big of a pump do I need? Well, for most guys, believe it or not, this 2 CFM pump here would be adequate for up to 5 tons because the hose and the conductance speed become the limiting factor most of the time for all those types of systems. 5 CFM pumps good for up to 10 tons. And for larger units, like we get into centrifugal chillers and things like that, an 8 to 12 CFM pump will get that job done just as quickly as a 50 CFM. Going to a larger pump does not help us at all on here because the conductance speed of the system and the conductance speed of the hose. Now remember earlier we talked about the deepest vacuum we can get is negative 14.696 inches of mercury. So this 2 CFM pump, and I have a 12 CFM pump over there, neither one of those pumps can pull a deeper vacuum than the other. They're both going to pull that negative 14.696 inches of mercury. And because they can't, we're bound by physics on that, because they can't create a lower pressure than that, the only thing that's going to increase the flow is the hose size or the connected tubing that we're connecting to. And for this fact, most of the time, the refrigerant lines are too small or too long that they're what's creating the resistance to the gas flow. And then the manifold hoses, if you're using the right hoses, usually become the second limiting factor, if not the first. So those are important things on there. So when you're buying a vacuum pump, bigger's not better unless you have the correct manifold hoses and you have tubing that will support the conductance speed. All right, so let me give you an example here. I have a 12 CFM pump versus a 2 CFM pump. The 12 CFM pump, when we go to the next screen, will be the black line, and the 2 CFM pump will be the blue line. The 12 CFM pump has a 5 micron ultimate pull. So this is an industrial pump. It's got a much better rating than the 2 CFM pump at 10 micron. That's only 5 micron difference, but in the world of vacuum, that could be a little bit significant. So I wanted to point that out there. What I'm showing you is basically that the 2 CFM pump, the really, really deep vacuums is not going to outperform that 12 CFM pump. And the question becomes is how much faster will this 12 CFM pump be? Now, mind you, I've got this connected with a 3/8 hose into a standard 4-valve manifold. 3/8 goes to 2/4 inch. I've got the True Blue connected directly on a stainless steel tee directly to the tank. And now we're going to compare these things side by side and see how much faster the 12 CFM pump will be. Well, it's not, at least not for long. And let's look at what happened here. So when we first start the evacuation here, and this is about a minute in, you can see both pumps, the black line, the standard line, the standard pump, excuse me, the 12 CFM pump starts pulling down a lot faster. So it actually starts pulling down faster, and then the True Blue comes in right behind it. And it holds this way until we get to about 2,000 microns. Well, the question is, why is this? Well, initially when we have the 1/4 inch hoses, what we're seeing is that we're able to pull down much, much faster because the hose is not the limiting factor, right? We have all this pressure in that tank, and that pressure can push through the 1/4 inch hose, and the hose can move more than 2 CFM of flow. On the smaller pump, the pump now is the limiting factor. So even though we're tied to the larger hoses, the pump can only move 2 CFM. Now, once we hit about 2,000 microns right here, something starts to happen. And what happens there is they first of all start to converge, and then the True Blue actually starts to pass. Now, why is this? Well, once we get into a deeper vacuum, the hose becomes the limiting factor, not the pump itself. So even though I have this 12 CFM pump, initially it could outperform the 2 CFM pump. It was because the 2 CFM pump was a restriction. But now we get in a deeper vacuum, it becomes the hose that's the restriction. And this really, really becomes significant because our ultimate goal here is to get down to 500 microns. So we can see here at about 6 minutes with the True Blue we crossed for the 1,000 micron mark versus about 7 minutes. So about a minute difference or so. That's a little bit interesting. But you can see here at about that same 7 minutes, we crossed 500 microns with the True Blue hoses. And then if you go clear out here to 15 minutes is where we crossed with the standard Hillmore gauge set and a 12 CFM pump. So you can see we're substantially faster when we go into deeper vacuums with the True Blue rig and the 2 CFM pump. And this is the big reason when you're ever going to buy a pump, you need to make sure that you connect it to the right kind of hoses. We can make that 2 CFM pump perform just as well or better than a 12 CFM pump simply because of the rig that it's attached to, and that's one of the big reasons you want to use True Blue. Hose size really matters, right? A 3/4 inch ID, and this is a 1 inch OD hose. Spring reinforced, super smooth interior, very, very flexible. If you stepped on this hose or drove it over with a tow motor, you could knock it round if it got flattened out. And it's 96 times faster than 1/4 inch hose is at about 500 microns. Really, really long life with reasonable care. And it's, again, engineered for vacuum. And just to put this in perspective, this is a 1/4 inch nut off the hose. It's so big I can slide it right inside there. Now, one other question we always get is, what's the function of the pump ballast, right? And it's not to just crank it shut with your channel locks and close that thing off. Liquid water destroys the usefulness of the vacuum pump oil by increasing the vapor pressure. So here I've got a demonstration here. We're pulling the atmosphere, and this is the first stage of the pump. And then here it pulls into the second stage of the pump for second compression. Now the gas ballast coming in from here on the side is injecting a small amount of air into the vacuum pump as it leaves the second stage. And that small amount of air is simply to dilute the moisture that's been collected in the vacuum pump oil. So the pump, if the pump gets contaminated with water, it can't create the vapor pressure higher than that of its sealant. And the oil is its sealant, so it just starts to, the oil doesn't work as well and we can't get our deep ultimate vacuum. The ballast injects air into the second stage of the pump to dry out the condensed water and the oil. Now here's the thing you need to know. The ballast works from 20,000 microns down to about 2,000 microns. So you want to start with your ballast closed in your pump. Open it up at 20,000 microns and run it till it hits 2,000 microns. And then you have to close the ballast off to attain the ultimate vacuum of the pump. Now the only time this is really important is if we have a wet system. If we have a dry system, you can leave the ballast closed all the way through because it's going to pull down so fast you're going to be in an area of 2,000 microns in a very, very short order, so it doesn't make much difference. Now we're talking about desorption. Desorption is just simply dehydration. We talk about absorption is like a sponge absorbs water. Desorption is just the opposite of that, it's dehydration. Every time a system's open to atmosphere, we have a large amount of relative humidity that covers the surface. Everything in this room has got relative humidity on it, right? And as we draw a vacuum, what we're doing is breaking those bonds, those water bonds, and pulling them out here. Now the reason I pulled this graph out here, this is this is hours to dehydrate a system. This is bake out versus ultraviolet versus natural removal. This is 10 to the -3 torr, or 1 micron, okay? So you can see this is 0 hours. So down at this 1 micron level here, it's starting at the 0 point. When we talk about desorption, it's a phenomenon where the moisture is released from the surface. But when we're in this low micron range, that water makes up 99% of the total gases. In the ranges we're working in, we're so far above 1 micron that the moisture, most of the moisture we're concerned with is out early on in the load. So that moisture can be removed in very, very short order. Now here's the key thing we got to remember though, is that if we have liquid water in a vacuum, okay, because water cannot be removed from a system unless it's turned to a vapor. All right, a lot of people don't understand that. Vacuum pumps just create a reduction in pressure. There's no flow in a vacuum per se. It's just there's the pressure, you know, it's traveling from high to low. We're creating that low zone. But when I say flow, what I mean is there's no flow that's going to carry the water along with it. Okay, think about if I were to put a cotton ball and stuff it down inside of a Coke bottle, right? Drop it down to the bottom there. No matter how hard you suck on that Coke bottle, you can't lift the cotton ball up. It's just not going to move. There's a reduction in pressure in there that's going to keep reducing the pressure, but the cotton ball is not going to lift because there's no flow, there's no air coming in behind it to carry it through there. Now if we put a teaspoon of water inside of a system, just 1 teaspoon, that's 0.0092 pounds of water. At 212 degrees, that would occupy 0.24 cubic feet of space, right? We drop that down to 32 degrees. That goes up to 30, from 0.24 to 30 cubic feet of water vapor. At 20 degrees, it's 51 cubic foot of water vapor. At 0 degrees, it's 138 cubic feet of water vapor. Think about what's going on there for just a minute there, okay? When it gets cold in the wintertime, you're doing an evacuation. This is why it takes so long to evacuate the system, because there's any moisture in there, the colder that moisture is, the more time it takes to remove. Now that 1/4-inch hose that we're talking about using, with 1/4-inch hoses and a, let's say a field piece VP85 8 CFM pump that's choked down to 0.2 CFM, that would take you 11.5 hours to remove that little tiny bit of moisture. A teaspoon, 11.5 hours to remove it, right? This is why some evacuations seem to take forever, because it takes so long. With True Blue and an 8 CFM pump, we could get that same moisture out in half an hour. And here's the math right here. It's just simply 138 cubic feet divided by 0.2 divided by 60. The 60 is to just convert the CFM, cubic feet per minute, to hours. 138 divided by 8 divided by 60, half an hour. So you can see again, when we get that moisture in there, having the larger hoses is also going to help with moisture removal. This is a graph here. This is what a wet system looks like. So you can see when I isolated here at 500, it went back up to 1,000 real rapidly. I pulled it down again. It went back up a little slower, pulled it down again, went back down even slower, pulled down again. Eventually here it's passing, because my decay target is 1,000 microns. What this is showing us is as it's wet and it's drying out, the vapor pressure builds up slower and slower and slower as we go, right? And this is just a graph here. This is where this information came from. Vapor pressure and specific volume versus water and temperature. All right, so that wraps up evacuation 201. Now we're going to get into the process of vacuum 301. And so there's a process for the fastest evacuation, and what I cannot stress enough is to keep the piping clean, dry, and tight. This means that when you're doing your brazing, you're sweeping that with nitrogen or CO2, and you've actually swept it the entire time, and actually before you ever pressurize it, we're also sweeping that, because it's really, really important. I'll cover that in the next step up here. We're going to pressure test with only nitrogen or CO2. We never ever pressure test with air or oxygen. If we pressure test with air or oxygen, we could have other things like an explosion that we have to deal with. So always pressure test with inert gas. When we vent that pressure off, we're only going to vent it down to about 1 psi. So what we want to make sure is that when we pressure test, we take it down to about 1 psi. We do not want to let it go all the way down to atmospheric pressure, because we don't want that moisture flowing back in. As long as there's a positive pressure in the system, we're pushing that nitrogen out, no moisture can enter in. We want to start with clean, dry vacuum pump oil. And my recommendation is always perform a single deep evacuation. I'll tell you a little bit about triple evacuation a little later on in the presentation, but there's no reason we need to do a triple evacuation. We want to pull below and hold the target for a thorough dehydration. We want to get that moisture out of the system. We want to isolate and verify acceptable levels, and then document via a screenshot or report. So this is a really nice crisp pull down here. As you can see, we pulled that system down, and at about 5 minutes, we're down below 250 microns. I isolated it, which is this little bump right here. And then when I isolate it off, this is 20 minutes out. You can see that slow, small rise, and that's less than, actually it's showing 0 microns per minute, which is 1 micron permissible rise. You can see we're nice and flattened out right there. So that's the type of evacuation we want to see. Vacuum pump oil, again, it's critically important. You want to make sure that you have a vacuum pump oil with a vapor pressure not greater than 5 microns at 100 degrees Fahrenheit. The pump cannot create a total absolute pressure deeper than the vapor pressure of the sealing oil. So oil is what's used really to create a big part of the vacuum. You cannot use refrigerant oil. If you're out of oil for your vacuum pump, don't pour in motor oil. Don't put in vacuum refrigerant oil. You've got to use a high quality vacuum pump oil to be able to pull a deep vacuum on the system. On small pumps like this, we should really change the oil after each use. On larger pumps there, you can actually change it less frequently, and you can use the ballast to remove moisture. But you always do want to change your oil on your pump, because even though we're pulling out and drive out a lot of the moisture, what we can't always get out are some of the acids and other things in those oils. Eventually the oil does go bad, it does need to be replaced. Pull out the valve cores. If you have a 6 CFM pump and you leave that core in, you just choked it down to 0.2 CFM. Even if you're using our True Blue hoses, you're going to choke that down there, because that core is a huge restriction to evacuation. With the core removed now, we're at 6+ CFM of flow, right? And that 6+ CFM depends on the level of vacuum we're at. And I think this is 6 CFM at maybe 100 microns on there. But you can see here when we pull that core out how much that opens that space up on that system. Use dedicated vacuum hoses. This one, again, really, really important. We talked a little earlier, these are the competitive hoses here. They've got pinpricks here. I've circled them there so you can see those. Pinpricking a hose cover permits trapped gases or vapors to escape from the hose carcass, right? I think it's called a carcass because this technology is dead. Steam, air, and other gases can permeate, pass slowly through the tube, and will build up in the reinforcement area, so the manufacturer must pinprick the cover on certain hoses. Now, why is this pinpricked? Because it's a repurposed charging hose. And guess what? If it leaks out, it also leaks in. And this is a huge problem. Freon charging hoses are charging hoses. Again, they're very gas permeable. We got all the oil to deal with. You don't want to use these hoses. They're way too small. We've already discussed that in an earlier video, but they're not the right type of technology in there. And it's really, really important that you use an engineered solution if you want to get the fastest vacuums and best results. Micron gauges. You've got to have a micron gauge, okay? You cannot determine proper degassing and dehydration using a compound gauge. You know, here, this is 0 to 30 inches of vacuum, right? Well, if you're looking at your inches of mercury, can you tell the difference between 29.14 and 29.916? No, nobody can see the difference on there, right? I mean, and that's the difference between 20,000 microns and 100 microns. You cannot tell the difference in there. You can't tell by the sound of the pump. You can't tell by time. You can't tell by pressure rise. You can't tell by pressure testing. You just can't tell how much moisture you've got in that system without a tool like a vacuum gauge. It's absolutely impossible. Remember, it's 2 steps, degassing, dehydration. So we're trying to quantify how much moisture we have in that system. You've got to use a good vacuum gauge to do that. When you're looking at vacuum gauges, I want you to look for the following. High accuracy, very, very important. We need to know where we're at in that vacuum. High resolution. Resolution means how much can we resolve. With this Pro gauge here, it can resolve down to 1/10 of a micron, okay? Temperature compensation. We want to make sure that we have a gauge that's engineered to work in the temperature extremes we work in. The old thermal engineering gauges were not temperature compensated, so they were good at 500 microns at 70 degrees Fahrenheit. That is it. You get away from that temperature, the gauge is no longer accurate. Leak rate indication. We want to know how fast is our vacuum decaying in microns per minute, because there's a permissible leak rate. Pull down indication, how fast are we coming down? Built-in diagnostics, is the vacuum gauge oil contaminated? Is it calibrated? Is it accurate? Field calibratable. Most of you guys never know if your gauges are accurate or not. You have no way of calibrating them. So you want to make sure you've got something you can calibrate. Factory rebuildable. These are not throwaway gauges and can handle high pressure. This gauge can take up to 1,000 psi. 1/10 of a micron resolution. It does have the pull down indicator, the leak rate indicator, and the rise time indicator. You'll see gauges like this. This thing's got very low resolution, and it hides all the decay and it hides the leaks in the system. This thing's got 1,500 microns to 1,000 to 750, right? If I get down here at 500 microns and I'm watching a decay test, but from 500 to 750, I don't see anything. I have no idea if it's even doing anything. So this hides all of those characteristics, the things that we want to see in a vacuum, it hides. The old thermal one was really cool because with an analog needle, we could actually see the needle continue to move up or down there. But again, it doesn't have that temperature compensation, which is so critical to know how far in the vacuum that we really are. Avoid improper attachment. We already talked about small diameter hoses. We already talked about length being a big factor in there. Avoid refrigerant hoses. Avoid the manifold. You do not want to be connected here. I got a yellow jacket manifold. We're pulling through this. Absolutely the worst way you could do vacuum. This is tied in with a vacuum gauge in line. Again, reading at the wrong spot and using the wrong types of hoses. You want to attach it with a non-permeable brass connector like this one. Avoid connecting the vacuum gauge to the pump, right? Again, here we're connected to the manifold. I don't want to know what the vacuum is in my manifold. I want to know what the vacuum gauge is in my system. Here I've got a long 1/4 inch hose to the vacuum gauge over here, right? I got six foot of hose here tied to this vacuum pump. I can move that pump all the way up right to the system there and really make that hose much more effective on there. right? You'll see some pumps that have built-in Micron gauges or roughing gauges. Okay, that's really cool, but only to see how deep the pump will pull. That's not a gauge to look at how deep your system is. Well, you can valve that off. You can look at how well the pump pulls, make sure it works. With a roughing gauge, you can't tell too much of anything, but it's okay to have that gauge on there as long as it's not your only gauge. And even a lot of the manufacturers have not gotten this right here. We're showing a 4-valve manifold system. We're connected through the manifold. Again, eliminate that. All this is excessive hose. We don't want to deal with that. And this is a ton of different leak points we have here. If a hose is loose or anything like that, we want to eliminate all those leak points on there. This is how you should attach your vacuum pump. This is a huge system. This is a 2,500 ton centrifugal. Notice that I'm doing the evacuation with a single hose on there, just one hose. Short, large diameter hose, valve cores removed, direct connection to the pump, core tools to isolate the system, gauges connected directly to the core tools, and vacuum rated hoses. Here's a residential system. I'm pulling from the high and the low side. Whenever we can, we want to pull from high and the low side. In this case, of this commercial job, it doesn't matter because the conductance speed of the system, the interconnecting tubing is so high that it'll pull down without having it connected to multiple points in the system. This one, I'm dealing with 2 small pieces of tubing, and I can pick up a little additional speed by connecting to 2 points in the system on there. Deep vacuum method. Evacuate the system to at least a depth of 2 times the allowable decay. So in this case, if my target's 1,000, I want to at least get down to 500 microns, right? 500 times 2 is 1,000 microns. 500 allowable decay, pull to 2 to 250. And ideally, what I'd like to see you guys start doing is pulling down to 100 microns or less. And that will create an adequately dry system. A decay test is used to determine the system's been properly evacuated, and a rise of 1 micron or less is generally permissible. So here you can see when I pulled this down, it leveled right off, okay? 0.0 microns per second a rise. That system's nice, dry, and tight. Here's a system that's wet and drying out. We pull it down, we isolate it, builds back up in vapor pressure real quickly. There's water in there. Those water molecules are expanding, occupying the full space of the container. It builds up really quickly. Pull it down again, it builds up slower. Pull it down again, it builds up slower. Pull it down again, it builds up slower yet. Eventually it passes here, right? Big difference on the 2 systems here. One is a dry system, one is a wet system, but both systems, and you can tell here, this took 1 hour and 15 minutes to dry out this system. 1 hour and 15 minutes versus 5 minutes to pull that down into a deep vacuum when it's not wet. You keep that tubing dry and tight, your evacuations will fly. You leave that thing wet and open to the atmosphere, you're going to take a longer time no matter what you're using. This one was really wet. It had actually standing moisture in it, but you get the idea of the difference there. Triple evacuation. This is often called the sweep, dilution, blotter method of evacuation. It's based upon using a dry gas to blot up and carry away the moisture in there. And this was used when the vacuum rig and the system could not achieve a deep enough vacuum to do the job on its own. This goes back to single stage vacuum pumps, okay? There's no reason we need to do this. It's a waste of time today. The first 2 pull downs were done at 27 inches. In fact, this is out of Carrier's guide right here. You can see they're showing inches of vacuum here. They're not even showing, at this point, microns of mercury because, again, this is older pumps, older technology. So here they pulled this down to 27 inches of vacuum. And then they waited 15 minutes at that range and then broke the vacuum and waited an hour. Pulled it back down again, 15 minutes, waited an hour, back down again 15 minutes, and then charged the system. So you can see here, this triple evacuation, you're talking about 45 minutes here and 2 hours. So 2 hours and 45 minutes to evacuate a system. You literally do not have to do that with one quick pull down on the system because I can get down to 100 microns in very short order, and I can assure you that system is nice, dry, and tight. Now, this is not a bad process if you have a system that you know is wet and there's standing water in there, because if we pull down really fast, especially on refrigeration systems, or it's winter time and it's cold out already, we could freeze moisture in the vacuum lines. This is very unlikely, if not impossible, for most air conditioning applications. You think about it, we're doing evacuation at 70, 80 degrees outside. There's so much heat in that tubing that it's gonna warm up that water as we evacuate it. It's gonna boil away so fast. Now, if we got into a deep freezing system where we had standing water, then this will help accelerate the time that it takes to get the system evacuated. But what you're really doing, this waiting an hour, is waiting for that water to evaporate right? Waiting for the water to evaporate, and that's what we're using the nitrogen as gas to help carry it out. Nitrogen can only hold water vapor. It does not absorb it, right? So if we have liquid water in the bottom of something, we put dry nitrogen in it, the dry nitrogen is not going to swing by like a sponge and grab that liquid water off the bottom and absorb it. It just doesn't happen that way. It's a waste of time, though, on a dry system. So let's talk about that for just a minute on that water vapor. Let's talk about a couple myths that are busted. Now, air or nitrogen does not hold water vapor. We talked about that earlier. It doesn't absorb into the nitrogen. The water vapor simply resides in the empty spaces. So nitrogen acts as a carrier. When that water vapor gets in here and I blow that nitrogen out, I carry out some of the moisture with it. If there's any standing moisture in there, then it doesn't go anywhere. Now, we talked about also when air is compressed or cooled, the water molecules fall out because of the space between the molecules. This goes back to what I was telling you earlier, first part of the video, vent or sweep the system with nitrogen before you pressurize it. If there's a bubble of atmosphere inside that tubing and we can press it down, right? It's just like this air compressor here. The water, the liquid will go from a vapor, it'll drop out in liquid. Once we get liquid in the system, it takes forever to remove. So we want to avoid that at all costs, okay? So very, very important to do nitrogen sweep first. And then again, the only thing that water molecules can do is as a vapor, occupy the empty space between the nitrogen molecules. When we blow out the nitrogen, we'll carry out the water vapor with it. But if there's any liquid in the bottom, it's sitting there until it evaporates. When air is heated, the space between the molecules increases. Therefore, there's more space for the water molecules to reside. That's why you talk about hot air can hold more humidity than cool air can. And water vapor and air are two gases that are completely separate from each other. Some properties of moisture. We're going to talk about cohesion and adhesion or absorption. So the process of degassing is oxygen removal. It also causes what we call dehydration. Now here's the things you need to understand. Water sticks to water. That's called cohesion. And water sticks to stuff. And that could be stuff, could be like the inside of this tank here. And that is called adhesion. So water is adhered to the outer side of this tank here. If there's a little puddle of water, there's cohesion. The water molecules are sticking together, sticking to each other. Adsorption happens right at the surface, right? And lowering the vapor pressure as we draw a vacuum on this tank, it's going to break these bonds of moisture away and it's going to start to dehydrate that tank. If we heat up the outside of this tank, it's going to help vaporize those water molecules away. A decrease in temperature, though, becomes a vicious cycle because as we start pulling a vacuum on this and this water in the bottom starts to boil, it absorbs heat from this tank. And as it absorbs heat from the tank, it gets cooler. As it gets cooler, it takes more and more space or more and more space up in the tank. We call this specific volume. Earlier, remember we talked about how the specific volume increases as the temperature goes down. The cooler this water gets, the more space it occupies. So this, again, is what causes that whenever we have water, standing water in the system, why it takes so long to get that evaporated out of there. How low should you go? Vacuum for service engineers, 59, I think we said earlier in the video here, right? Old science. Finishing pressures of 1 to 200 microns are desirable to make this system, to make the air in the system so rare that there's only an insignificant amount of weight left for the refrigerant to absorb, thereby establishing good control over the subsequent head pressure of the compressor. Think about that for a minute. I doubt anybody here in general has pulled down microns to 100 microns as general practice. Yet that's where we should be going. Here's a system, this is a 5-ton system here, 99.8 microns, final vacuum 99.8, 12 minutes and 19 seconds to get it down there. Comfort cooling new installation, we want to pull down between 100 and 200 microns. The copper should be dry, should be tight, this should be very, very easy. And we don't want to decay over 500 microns. And really, this will flatten right out. You really won't get a decay much over 130 microns most time. Comfort cooling service equipment, 250 to 500 microns with 1,000 microns max. Now, when we're talking about service, where it's the system that's had refrigerant flow through it. We've already evacuated this once. Now we got refrigerant, we got oil, we got other things to deal with. We're not going to be able to pull that system as deep as fast. And a lot of times we're relying on the dryer, that we're cutting out the dryer, replacing it, put a new dryer in there. We're relying on that dryer to remove any residual moisture. General refrigeration, 100 to 200 microns, 500 microns max decay. Ultra low temp, 50 to 100 microns, decay 200 microns max. Again, what we're talking about now is moisture. When we get into that negative 40 on ultra low temp, we cannot let the micron level go up any higher. Some manufacturers will tell you got to be below 100. Some will tell you below 50, right? It all depends. When you get into ultra low temp, it depends on how far down you're going. Transport refrigeration, or things we see with mechanical seals, you don't want to pull much below 500 microns or 1,000 microns decay max. The mechanical seals just don't seal as well as a hermetically sealed system. Can you vaporize oil and damage the compressor? No. Okay, you just can't do it. You can pull out moisture, you can pull out gas, refrigerant gas, but you cannot vaporize the oil even at 30 microns. The vapor pressure of refrigerant oil is far too low. When you see bubbling of the oil, it's typically emulsified refrigerant or emulsified moisture. It's mixed in with the oil and we're just boiling it out of there. But it's not the oil evacuating. Manufacturers consistently pull down into the 100 micron range when they're doing this kind of stuff. I've seen systems down as low as 30 microns and the oil looks just like this, just as still as could be. We're not going to evaporate the oil in the system. That is an old wives' tale. It's bad information that came across the industry. When we do the isolation, this is isolate the decay test, okay? There is actually a standard. Again, the review of vacuum for service engineers. The permissible pressure rise is generally set at a raise of 1 micron per minute with a finishing rate of 1 to 200 microns desirable. I'll click this video here. You can see it, we're opened up. We start closing that valve off down in the bottom. We're at 135. The micron range is rising up to 153, 157, 160. This is a decay rate we're looking at. And eventually that's going to go up very quickly and then it's going to flatten out and we can see what our ultimate vacuum is. So we're testing the tank now to see how far down that has held and what the actual vacuum is. You cannot test vacuum on a system unless you isolate it. You have to close the core tools off and actually see what the evacuation is, right? Also, with the app here, I'll show you the app here in just a minute, it takes the mystery out of evacuation. You can't tell on a standard vacuum gauge whether you have moisture or a leak. And TrueBlue is one of the only systems with a BlueVac Pro that you can actually do this. What we've done here is we pulled down, we're down here about 400 microns or so. We isolated off. You see this straight up rise and then this continual rise. This is indication of a leak. This is over time. So the only reason this is at a small angle here is because it's over time. If we took the time factor out, this would literally be going straight up. It'd just be a straight up leak, okay? Now notice here we pulled down, we isolated it and it tails off. Tailing off means that the vapor pressure is gradually building up. It gets to the point where the vapor pressure equalizes in the system. This is right about 2,500 microns, so this is a good indication of moisture, 2653. So you can see here, this has got a decay rate of 42.7 microns per second. After this is stabilized here, this is looks like about 8-9 minutes, the decay rate is at 0.8 microns per second. So this is not continuing to rise, it's leveling off. With that, it's just a continuous leak. So it allows us to stop moisture in its tracks. After you're done, you're going to document the job well done, right? We can pull this down, we can generate a report. It's going to show us the total elapsed time, the time to ultimate pull down. It's going to show us where we pass, fail, what our ambient temp was when we're doing the evacuation, our final vacuum where we isolated off, and then the device serial number that we're using here. And this is a really, really good way to document your evacuations. So now I want to get in here and talk a little bit about the results, way faster evacuation times and longer system life. This is a 2,500 ton York chiller at the University of Kentucky. There's a video that Andrew Greaves and I did on this. This thing is about the size of 2 buses. I mean, it's a huge, huge chiller here. About a 30-inch suction elbow. Evaporator and condenser lengths are, like I said, about the length of a school bus. Typically, they would take 4 to 6 days to perform this evacuation. We started this at 4:30 in the evening, and we came back the next day. We thought we'd be down, so far we didn't have any idea. But we did that with a single 3/4 inch hose in about 17 hours. And how far down did we get? Well, one hose, 12 CFM at the pump, no oil changes. We literally started overnight. 121 microns at the pump, 314 microns at the far side of the system on there. So you can see, 121 microns down here at the vacuum pump. We put 2 gauges on there so we could see our pump performance. Put another gauge on the far side of the system so we could see You can see me standing next to this thing so you get an idea how big it is there, how physically big. 12 CFM Navac pump here, connected with one port directly to the system, and we got that system down sub 300 microns in, again, 17 hours. Residential system, this is a 100-foot, 3/4, 3/8 line set, existing line set. Cleaned it with R11 flush, so this was a replacement job. It had a 4-ton evaporator coil, 8 CFM pump, 5 minutes. Did less than 200 microns on that system. 5 minutes, start to finish, right? So again, what would normally take that contractor an hour to do, we got done in 5 minutes. So a substantial time in the savings in the evacuation. Oxygen and moisture are the absolute enemy of a system. Oxygen's an oxidizer. It's going to cause corrosion. It's going to cause things to get eaten up. It turns the oil black. In this system here, you can see all this black gook in here, and that's all oxidation. It's oxidation of the oil, the hydrocarbons, and it can actually vaporize the motor windings in here. This is where we get a bunch of nasty stuff. If you leave oxygen or moisture inside of a refrigeration system, it's like a miniature chemical plant. It's constantly manufacturing acids and sludge and all kinds of gook that's going to just ruin that system. Plus, these acids are so powerful that they actually strip away the copper that's on the line set and redeposit it on the bearings there, right? So that acid stripping redepositing is what causes the compressor to get tight. It's what causes things just not to work right. Dryers can help a little, but the destruction is continuous. So you want to get all that moisture and oxygen out on the front end of the system. Internal formulary corrosion of copper. This is also called ant nesting. There's only a couple things that cause this. You've got to have oxygen, you've got to have moisture, you've got to have copper, and you've got to have organic acid. If you have those substances out there, you're going to get this, you could get this formulary corrosion on there. This is showing it from the outside in. It can also happen from the inside out, and it's typically found in copper and copper alloys. And then once you get rid of one of these components, if you get rid of the oxygen, the water, the copper, the organic acid, the formulary corrosion stops here. So if you want to avoid that from happening from the inside out, a good evacuation is the way to do that. What I've got here, I've got a 5-ton evaporator coil, and I've got it hooked up with 50 foot of 7/8 tubing and 50 foot of 3/8, so 3/8 by 7/8 line set. I've got it hooked up with our True Blue hoses. I've got this line here, it goes, it's a 3/8 line, but it goes right to the 7/8 tubing on the far end. And then I got the 3/8 connected over here. So we're pulling on both sides. I've got the Micron gauge hooked up at the evaporator coil, right at the outlet of the evaporator, so I'm about as far away as I can get from there. I've got this system wide open. I got the cap off here. So I'm going to go ahead and cap that. And we'll go ahead and do a pull down here, and let's show you how fast that we can do this as we go. So there's a few things here. I'm going to actually start out, I'm going to go back here and restart the recording, and then I'll kick on the pump here. So we're at 760,000 microns. We're at atmospheric pressure here. So the pump is a DC pump, so it's got a soft start. So you heard that start a few seconds after I did the switch. That's getting up and running here. And in a few seconds here, now remember we're at 760. Now we're just down to 120,000 microns, 48,000 microns, 29, 25. Now remember I told you before, all that traffic, 760,000 microns, we had a huge amount of air density, and how it was only going to take a few seconds. We're at 30 seconds in, we're already at 6,000 microns. So those quarter-inch ports, they aren't even a factor, right? Because we pulled down so fast, so far beyond that, that those aren't a factor anymore. So now we're down to 2,000 microns, 43 seconds in. Let's look at the graph on here. The graph we're pulling down, you can see how quickly this is coming down here, 1,800 microns. This system is very nice and dry, so we're going to give this a couple seconds here. I'll let this go all the way down until we get 100 microns on the evacuation. Now on the app here, what we're showing here is a couple different things. Up at the top here, this is a lot of oxygen and a lot of moisture. So this is the red range. This is where we want to be out of. We get into this portion down here, it's starting to dehydrate. And then down here in the dark green section is where we're really nice and dry on there. On the gauge, we're showing you a couple different things too. The ambient temperature in here is 75.3 degrees. Our pull down is 13.1 microns per second. We can also do that in microns per minute. I can go in here, I'll change the settings on here so we can see this decay in microns per minute. So we'll scroll down to the bottom here, app settings, gauge. And we'll change this to microns per minute. We'll hit check on there. So now we're at 430 microns per minute. So we have a really, really fast pull down here. We just crossed 500 microns. We crossed 500 microns at 1 minute and 45 seconds in there. So literally 5-ton system, 50 foot of 3/8, 7/8 line set, and in 1 minute and 45 seconds we're down to 500 microns, and you can see we're still going at 239 microns per minute on our way down to 100 microns. This is our saturation temperature. This is the boiling point of water. We're at negative 23 degrees. So again, this system is really nice and dry, and we're coming down quickly on that. We'll give this a couple more minutes to come down. The graph here, when it hits this point here, it's going to rescale. So we saw it rescale there, and we're still on our way down. Now, in the front of this, if we go back to the home screen on here, you can see we got a target here. This is our final finishing vacuum. So you can see this is coming down. We're in a dry section here. We're at 266 microns. We're in a dry section. We're approaching this target down here of 254 microns. So let this keep coming down here. A couple more seconds, we'll be down, and we'll be good to go. All right, so we're down to about 110 microns. You can still see we're pulling down at about 23 microns a minute. We're going to be down here at 100. And again, I want to be at a finishing vacuum of 100 microns. Let me just scroll through ahead here so you can see here. We are 5 minutes and 53 seconds. So in 6 minutes, we got a 5-ton system pulled down to 100 microns here, which we probably crossed at this point now. And there we are at 102 microns. 101 microns, so I am down. This is as far away again as I could get from the pump, so I'm at 100 microns right now. I just crossed it. You hear my gauges beeping here, so I'm going to go ahead, and it's telling me it's time to isolate the system. So I'm going to close these 2 valves off here, and when I close those 2 valves off, I'll just go ahead and kill my pump, and now I'm going to hit continue, and I got the system isolated at this point. Now it's telling me again now that I've got a pass here. I got pass on my gauge. And it's showing me pass on my gauge because it's calculating out what the decay would be. So you see a very, very tiny rise right here when I isolated this out. In fact, I can zoom in on that if you want to see that a little closer. So I have a very, very tiny rise on there, and this is starting to flatten out. Now there is a rise rate here, and right now it's at 11 microns per minute, but it's telling you that based at this speed that it's going to slow down or decay. The decay is going to taper off to a point where it's not going to matter. Because we have this set up so that it's going to in the app automatically to tell it to pass decay once it hits a certain point. So this will continue to rise up and slow down, and once it slows down and drops off here, then we'll know that that the system's passed, but otherwise the gauge has told us already that it's passing. You can see this is flashing between 10 and 11 microns per minute, and eventually that's just going to rise off and flatten right out again. But this decay part, what we're doing, we're waiting for that system because the pressures at each end of this tubing are much, much lower than they are at this gauge. So we're letting that pressure sort of equalize out. And as it equalizes out, that's what the decay time is. So now we're down at 10 microns per minute. If we let this go for 10, 20, 30 minutes, we'd see that would taper off to 0 microns per minute like I've shown you in the other parts of the video. So that gives you a really good idea here of what that looks like. We'll zoom back out so you can see how flat this line is here. So this is definitely going to flatten out. We're not going to get to this 500 micron mark anytime soon. You'll probably go out a couple of hours, and eventually it's just going to reach out and just flatten out, and it won't even rise anymore. But you can see now we're down to 9 microns per minute of rise, and that's our permissible rise rate is 1 micron per minute. But we can tell automatically with a gauge timer when this thing is with a gauge programming that it's right there and done. That vacuum sensor, that thermistor sensor, is just a little glass bead suspended on 2 wires, and that can get contaminated. Now, most of the time when you're opening a system up to vacuum, you know, like in this case here, I pull down the system and I get it down and I want to cut in the charge on there. A lot of times you don't want to take your vacuum gauge off because you're going to introduce air into the system. What I want to do is I want to always attach my gauge on my liquid line in my machine. Attach it to the high side, liquid line. And whenever I open up the porting, I want to open up on the suction side. And the reason I want to open up on the suction is because when I open it up, it's going to carry some of the oil out of the compressor and it's going in the suction line. When I start it back up again, I want it to suck right back into the compressor. Well, the cool thing is when that gas works its way around, I'm not going to carry the oil all the way over to the micron gauge. So when I don't carry it all the way over to the micron gauge, all I'm going to expose my micron gauge to is a small amount of refrigerant. Now, refrigerant will make the gauge read a little funny, but it will not contaminate it with oil. Refrigerant won't hurt the gauge. Oil is what contaminates the sensor. If you get a system that has a contaminated sensor, it'll tell you calibration is needed soon or maintenance is needed soon. And literally all you have to do here is take an eyedropper, take a small amount of rubbing alcohol, inject it into the sensor itself, put your finger over it, slosh it around, pour it out, and then put it on a vacuum pump, and it'll tell you that it's back to good on there. It's just that easy to run it through that process and clean it. So this is a calibration of actually, this slide should say oil on here. I guess I got a calibration slide on there, but it should tell you if it's oil contaminated or if it needs calibration. This is telling us it needs calibration soon. But if it's that oil, it'll actually tell you it has oil, and then it'll tell you when it's clean if we're good. All right, everything leaks, and this will be very apparent with your blue vac gauges. And what you're going to see here is that when you isolate the system, you're going to see that level of decay. You got a vacuum gauge that has a resolution of 0.1 microns on there. It's very, very seldom that you're going to see that 0.1 micron indication is going to stop moving on there. What we want to make sure is that our vacuum rate of decay is less than 1 micron per minute. That's the beauty of the Pro Gauge, is that we can actually let the computer tell us when the rise rate is low enough. But everything leaks. Our hoses leak, Appian hoses leak, quarter-inch hoses leak. It's the leak rate we're concerned with. Our hoses have one of the lowest leak rates on the industry. Vacuum rated means can pull down to, not hold. So here I've got this pump running, and I pulled down to 19 microns at the pump and 24 microns at the hose. I have a 5 micron difference in pressure between those two. Part of that is moisture in the hose that's boiling off still. It could be microscopic leaks in the hose, but we have a pressure difference between the inlet and outlet of the hose on there, but I can have 24 microns at my hose end. If you did this with an Appian hose, you might get down to 75 to 100 microns max. If you did this with a quarter-inch hose, you might get down to 400 microns at the deepest amount of vacuum. Each one of these hoses operates a little bit differently, but you've got to remember that the core tools that we have on the system, if you can zoom out for just a minute, the core tools that we have on here are designed to isolate the hoses. So when we close these core tools, I've isolated my hose, I've isolated my vacuum pump, I've isolated most of the things that can leak, and now I'm just testing vacuum here on my gauge, on my line set and on my system. These core tools, their design is to lock this thing off so we eliminate as much leak potential as possible. You cannot test the core tool on its own. You can't just hook a gauge to the end of your core tool and see if your core tool is tight on there, because that volume in there is literally an eighth of an inch diameter. It's so tiny that you're going to see that fast leak rate of your core tool. It's just too small, and the leak rate's too big to prove anything. You want to test your rig like I'm doing here for ultimate pull down, and the rig should pull within a few microns of the pump's pull. So you can see here, I can pull 19 microns at the pump, 24 microns. This is probably after about 10 or 15 minutes this is pulled down here that we achieve this ultimate vacuum level. But whenever we pull at the pump, should be very, very close to what I see at the end of the hose. I want to take all the work the pump is doing and move it to the end of the hoses. And again, that's one of the most important things that we can check is how well our rig works on there. So why True Blue hoses? Simply this: we get deeper vacuums faster. It's a large diameter hose, but not too large. We showed you got diminishing returns when your hose gets up to inch or inch and an eighth. It doesn't help us that much. Low water adhesion properties, meaning the hose is going to dry out very quickly. Very, very low outgassing, very low permeation. It's an engineered solution for vacuum. Nobody else in the industry is doing that right now. User configurable, meaning that all these ends can come off here. We can put quarter, half, 3/8 inch hoses on here, 90s on here. A lot of flexibility in how we use these hoses. They're also very, very flexible. Hoses can come in everything from our professional kit here with all the 3 hoses and all the fittings you might want to use, all the way down to our basic kit, which is just a core tool, half, 3/8, a quarter-inch connection, and some clamps. And this is what a lot of residential techs would need to simply pull a one hose evacuation on a system. AccuTools also makes a plethora of other products, including charging scales, leak detectors, vacuum gauges. Really take a look at the line. They've got some really, really innovative, dependable products out there. But this gives you a really good overview of what we have and what they have to offer. And again, you know, really what it comes down to is this: every measurement you make matters every single time. And again, this is Jim Bergmann with Measure Quick on behalf of AccuTools. Thanks a lot for watching.